Hey everybody, welcome to Quantum Mechanics for the Working Professional. This is our first problem solving session, and we're going to be going over the problems from section 1. I'm going to break this up into multiple different videos just so you don't have to watch them all at once. But for reference, you can navigate to the website, passaten.org, click on the hamburger icon and go to Courses, QMWP, that's Quantum Mechanics for the Working Professional, and scroll down to the relevant section. That would be 1, the Stern-Gerlach experiment. If you haven't found it by now, the bottom of the lecture has a bunch of exercises, and those are the exercises that we're going to cover today. So, in particular, we're going to start with problem 1. Use the column and row vector notation to compute inner products and explicitly verify the first equation. Make sure that you can pass between row and column vector notations with these. Yeah, great. We'll deal with a bit of that today, but suffice it to say that our first equation that we're looking to solve is simply the inner product up with down, down with up, and down with down. Okay, so let's get started. Before embarking into all of these explicit calculations of all these explicit states, let's first remind ourselves that these states are representing a quantum reality, right? Quantum configuration of a particle in a spin 1/2 system. That is to say, it's got an up state and a down state. That is to say, it's a 2-level quantum system. We have generically parameterized such a system by the vector or ket psi with two numbers, alpha and beta, where alpha is the multiplies the up state and beta multiplies the down state. This is our generic, if you like, quantum state. We have represented for this 2-level system our vectors as column or row vectors as well to make it easier to do computations. So for the case of the up state, we have defined the up ket to be the column vector 1 and 0. Similarly, the down ket is just 0 and 1. Likewise, we have the dual set of vectors, the row vectors, the bra vectors, if you like, where, for example, up was given by 1 and 0, and down is given by, again, 0 and 1. We can put these together to form a generic vector, psi, and represent that ket as alpha and beta, and its corresponding bra or dual vector or row vector, if you like, as alpha and beta. Now, why do we bother with having rows and column vectors? Because it makes it very straightforward to talk about inner products. That is to say, it's very straightforward to combine two vectors against each other. In kind of classical geometry, maybe you know the concept of an inner product, how you project one vector against another to get a sense of length. Similarly, you can ask what the magnitude of a vector is by taking its inner product with itself. Dirac came up with the bracket or bracket notation to make this easier to write down. But for the case of columns and row vectors, we know that psi with itself, psi is actually a number, which is the magnitude of the vector psi. And generically for any vector, let's say A with B, this is going to be some number that's associated to the inner product of the vector A with the vector B. Okay, so again, why we use rows and columns is because it's easier to do so. So let's imagine I have a row vector, A and B, and a column vector, C and D. We can combine them together as an inner product to form the number A times C plus B times D. This is just some arithmetic, if you like, some rules for combining the two vectors together. And this arithmetic generalizes to other kinds of objects, not just vectors, but also matrices. So for example, we can consider multiplying a matrix, let's say ABCD, times a column vector, let's say X and Y, and we can use the similar arithmetic, the same rules, if you like, for computing these component by component. So let's do an example. Here, given ABCD and XY, we multiply to find the first component is A times X plus B times Y. And the second component is C times X plus D times Y. So notice we started with a matrix acting on a vector, a 2 by 2 dimensional object, multiply that by a 2 times one-dimensional object, a column vector, and we end up with a 2 times one-dimensional object, a column vector. Similarly, we can arrange things so that a matrix acts on the row vector as well. What we'll find is that it acts actually on the other side. Now let's see how that might be the case. You might know that row vectors and column vectors are related by the transpose operation. So for example, given any vector, column vector x and y, right, we can use the transpose operation, denoted by t, to get us a row vector, which is the same components, only flipped on its side. We can do the same thing with a matrix. Let's say A, B, C, D, acting on it with the transpose operation, and that gives us A and D are in the same place, but B and C, the off-diagonal components, flip. If you want to get really technical, and this might go beyond the scope of a typical physics problem, you might consider a non-square matrix. Let's say like a 3x2 matrix, so A, B, C, D, E, F, and you can transpose that guy, and what you'll find is A, B, C, D, E, F. So it's the same thing, we just knock it on its side. One way to think about that is we flip the concept of a row with a column. Very easy. Okay. We're going to use this fact now to demonstrate how a matrix might act on a row vector instead. So recall that we just showed ABCD can act on the vector x and y to give us a new vector x prime y prime, where x prime is equal to ax plus by and y prime is equal to cx plus dy, right? So now let's ask, what is this primed vector transpose? Well, that's just x prime, y prime sitting on its side, right? But we also know that it's the product of a matrix times a vector. So we know that that is actually equal to A, B, C, D times x, y, whole thing transposed. So what is that whole thing transposed? What is it supposed to mean? Well, for us, it means xy transpose times ABCD transpose. Part of this arithmetic that we'll eventually learn, and you can prove if you want to, that when we transpose a product of things, we end up reversing the order of the product, but still applying the transpose. So, for example, in this case, we see x and y times A, D, C, and B. And now if we perform the calculation using the same rules of arithmetic, that is, you take the column and then you smash it against the row, in this case we're going to have to do that twice, we will find that this quantity is given by ax plus by, cx plus dy in the second component, which is nothing more than x prime, y prime. In other words, it's our primed vector flipped on its side, as advertised. So let me give you another hint as to why you would want to perform that rule of transposing products of things and flip everything around. So let's suppose that we have another vector, say v prime, given by many matrices acting on one little vector v. So let's say A times B times C times D times little v, where little v is a vector and A, B, C, D are now matrices. 2 by 2 matrix times a 2 by 2 matrix is a 2 by 2 matrix, which again is a 2 by 2 matrix, which again is a 2 by 2 matrix, which finally acting on a vector is now a vector, right? So let's proceed. So v prime transpose is going to be given by, according to this argument, v transpose times d transpose times c transpose times b transpose times a transpose. And let's see what we got here. In the first case, before we did any transposing at all, we have D acting on little v. And then we have C acting on D, acting on little v. And then B acting on that mess. And then A acting on that mess. In this latter case, we have the same pattern, just flipped, right? So we start with our little row vector V transpose. D transpose acts on that, then C transpose acts on that, then B transpose acts on that, then A transpose finally acts on that. So this is this reason where we're thinking now about row vectors is everything coming from the left side, everything coming from the right-hand side, as opposed to everything acting from the left. This notion of duality will come up again and again and again, and we will eventually get to the bottom of it. But for the purposes of this course now, at the present moment, suffices to say, these are the rules, and we follow the rules. Okay, so let's specialize now to the case at hand. That is to say, we wish to compute the following 4 numbers: up with up with down with up, and down with down. All right, so the first one is easy. That's just 1 and 0 with 1 and 0. That is, according to the rules, 1 times 1 plus 0 times 0, which is 1. Awesome. The second one is 1 with 0 times 0 with 1. That is nothing more than 1 times 0 plus 0 times 1, which is equal to, right, 0. I'm going to skip the third one for now and move on to the fourth one, down with down, which is 0, 1 and 0, 1. And that's just going to be 0 times 0 plus 1 times 1, which is 1. Great. Now, that second one, I'm sure you can already do, right? And we already know that the answer is 0, but I just wanted to point something out. And that is the transpose of these two vectors, the transpose of, say, up with down, is given by 0 and 1, 1 and 0. In other words, the inner product of down with up is just given by the inner product of up with down transpose. But you can't really transpose a number, right? It's just a single number. There's no diagonal components to a number, so it's really just the same number. So 0 transpose, in other words, is 0. Later, we're going to learn something about complex numbers, and we're going to learn about complex conjugation, and we'll learn about something we're going to call the adjoint. So that'll, like a Hermitian conjugate or whatever, and that will kind of augment what we mean by transpose, but only in technical terms, not in the spirit of things. But anyway, I just wanted to point out that those two kind of cross terms were related to each other by the transpose operation. Okay, great. So that concludes problem 1. Next, we're going to study problem 2, which uses these results in the computation of the probabilities of finding a particle in the state. Well, anyway, yeah, we'll get there.